Hello everyone. In this video, we'll be covering something additional that I thought it's best if students knew for physics electromagnetism topic, code 0625. So I've taken a look at the past paper questions, especially the more recent ones, and I've noticed a trend in the examiners incorporating a bit of the A-level, like very minute things from the A-levels into the CIE IGCSE physics papers. It could be in paper 4 or 3 if you're taking the core syllabus, or the MCQ papers. Now, I think it's better if the candidates knew these these things that are additional to avoid losing marks there, because at the end of the day, everyone wants that shiny A star, right? Or not judging you if you're going for any grade lower, but it's best to avoid losing marks in every possible question. So the two things that I'll be covering today are the Lenz's law. The first one is the Lenz's law. And the second one is power loss in cables. Okay. Now, firstly, let's take a look at Lenz's law. So what the Lenz's law states is that it's based off of the electromagnetic induction. That's the foundation. And what it states is the direction of induced EMF is opposite to the flux change that causes it. Now, this may trigger confusion, and that is completely fine. The first time I heard it, I was also very confused. But it stems from the induced EMF as aforementioned. So as most of you are aware, if you are not aware, I suggest you watch the previous videos for electromagnetic induction to get a basic understanding of that. So for a current carrying, not a current carrying, just a conducting wire in a magnetic field, if a force is applied to this wire, it will, when it cuts through the magnetic field lines or there's a change in magnetic flux, an EMF is induced or a current is induced. Either way is acceptable. So the direction of this current or EMF is given by the Fleming's right-hand rule. So in this case, if I were to apply force into the plane, so the force would be into the plane, the magnetic field, which is my index finger, would be pointing towards the right, and therefore the current would be downwards. Okay, so that is the basic principles of electromagnetic induction. Now we can take this a step further and apply it into coils. Now what do I mean by that? So firstly, let's draw a diagram of a simple bulb and a coil. It's not the perfect diagram, but just bear with me for now. So before everything, I'll just write the statement form. Direction of induced EMF opposes the flux change that causes it. I just wrote this because not everyone will have it in mind, so this is just here for you to refer to. Now what this basically means is that if there's an EMF induced in a coil or anywhere, the direction of the EMF will be opposite to the flux change that causes it. What do I mean by this? So most of you will also be aware, if you have watched the first part of electromagnetism, is that the right-hand grip rule, it can be applied for coils as well. So when there's a current carrying coil, your fingers that curls around gives the direction of the current, and your thumb, the direction in which your thumb points, is the north pole. So let's say this is the north pole and this is the south pole. No, sorry, let's say this is the north pole only, okay? So it's obvious that if this is the north pole and a magnet cannot only have one pole, it has to have two poles. It must be dipolar. So it'll also have a south pole. And these follow magnetic properties. Now, that would be the case if a current was running through it. But in this case, we are not running a current through it yet. We just have a bulb attached to it. How will the bulb light up? The bulb doesn't give out any current unless it does, which in most cases isn't the case. So you will recall again from electromagnetic induction that if there is a flux change, an EMF will be induced. Okay, so this is north and south. Okay, this is the magnetic field lines. It goes from north to south. Yada yada yada, you get it. And there's more as well, but we'll just assume that this is the magnetic field lines for now. Okay, so when this magnet, it obviously extends. There's more, and it's so big that it intercedes with this coil. So when this coil cuts through these magnetic field lines, so when this moves this direction, when this coil cuts through this magnetic field lines, an EMF will be induced, which is what you know from electromagnetic induction. What the Lenz's law and what this law states is basically the direction of the induced EMF. So by the direction of induced EMF, it says here that it opposes the flux change that causes it. What do you mean by this? So basically, if I were to say that this magnet is moved towards this coil, okay? Now when it's moved towards this coil, what happens is it'll induce an EMF, which will also, when an EMF is induced, there's obviously a current induced. And what happens when a coil carries, where a current carrying conductor carries current? It also has its own magnetic field, okay? Because it has its magnetic field, these two magnetic fields will interact and induce a force or apply a force on this magnet. So what is the direction of this current and the direction of this magnetic flux? That is what this law states. And well, the direction of this current is basically the direction of the induced EMF. So if I were to move this magnet towards this coil, it would oppose the movement of this magnet towards it. So it's opposite. So if the magnet is moving towards it, it opposes the magnet. So what does that mean? How would a North Pole be repelled? How would the North Pole be repelled? Well, obviously, if there's another North Pole, because like the like poles counteract. And if that's a North Pole, this is a South Pole. And how do you find the direction of induced EMF and therefore the current using this? Well, you use the right-hand grip rule. And you put your thumb near the North Pole, or the direction where the North Pole would point, and the way your fingers are curling is how the direction of the current and induced EMF, and that is this. Normally they have like a piece of metal here to amplify this magnetic field, and that is, imagine like this, the directions where I pointed where the arrows are there, that is like the front. So this is the direction of the current. I hope that makes sense. Now, fine, that's well and good, but what would happen if, let me just erase this. Now, what would happen if, how did that turn into a circle? Okay, so now what would happen if I were to move this magnet away from this coil? Now, as I told you, this magnetic field lines, it's only what I drew. It obviously extends way further. So even if it's moved away, it would induce, like it would be cut through, the magnetic field lines would be cut through. And when there's a cutting of the magnetic flux, that's when an EMF is induced. And this time you're moving the magnet away from the coil. And using this law, again, it states that it opposes. So when it's trying to, like when you're trying to move it away, a force would be induced, which would be opposite to how you're moving this, meaning this would be attracted. Okay? And if this is attracted, what pole would this be? So this would be the South Pole, and therefore this would be the North Pole. You point your fingers towards the North Pole, and the direction of induced EMF and the current would be like this. That is the Lenz's law. Now you don't need to know like the name of this law, you just need to know the statement form, but I suppose it's better to know as well. And the formula isn't necessary either, but I'll just write it here because why not? Anyway, let's move on. That is the first part. And the second part is the power loss in cables. Now, this doesn't have any statement form, but it basically applies to transformers, right? So a transformer isn't only limited to a bulb. Pardon the very poor calls. A transformer isn't always limited to a bulb, right? Uh, it it's it goes to power stations, so things that these things stand, and it's sent throughout everywhere. Now, this isn't a human being. What I tried to do here, what I tried to draw here, was the antenna towers, right? So it goes to these, and it's supplied everywhere, right? Now, oftentimes the candidates will be asked a question regarding the thickness of the wire, the length of the wire, and the power loss of the wire. So the questions usually are revolving why high voltage is used. So high voltage. High voltage. Why is a high voltage used? Or why a longer wire is used? Or why a thinner wire may be used? The third question is really rare. The second and third are lesser common than the first one. And this is where I also have a tip for everyone that always answers in terms of physics. And that is, so answering your first question, it's because if there's a high voltage, there's a higher resistance because V is directly proportional to R. So if there's a higher voltage, there's a higher resistance and therefore a lower current because R is inversely proportional to current. So when there's a higher voltage, there's higher resistance and lower current. Okay, well, what is the relevance of this, you may ask? And that is, how did that happen? How does this keep happening, man? Okay, and that is this formula. So P is equal to I square R. This formula is used to give the power loss as heat in the cables. So as you can see that it's directly proportional to I square. So the lower the I value, the lower the power loss as heat. So you're trying to be as efficient as possible when you're delivering the power over long distances. So obviously you will try to lower the current as much as possible. And that is why they use a higher voltage to reduce the power loss as much as possible. And the other thing that I'd like to mention is regarding the length and the thickness of the wire, right? So this is a formula that you must know. The derivations is not really important in IGCSE, but it's formula you must know, rho L by A, okay? Where R is the resistance, rho is the resistivity of the metal or the substance that's being used to make the wire. L is the length of the wire and A is the cross-sectional area. So you see that resistance is directly proportional to L and resistance is inversely proportional to the area. And always keep in mind that resistance is proportional to voltage and resistance is inversely proportional to the current. So as you can see, the higher the length, or the longer the length, to be precise, the higher the resistance and therefore the higher the voltage and the lower the current. So if you use a longer length, the current in the wire will be lesser and therefore the power loss to heat will be lesser. Same with area. Why a thinner wire is used of a thin cross-section area? It's because it's inversely proportional. So a thinner wire would result in more resistance and therefore greater voltage and lower current. And by this relationship, a lower current would reduce the power loss as heat. I hope everyone understood. That is all. If you have any doubts, please do leave them in the comment section below, and a like to the video would be very appreciated.